adult humans who have more brown fat, they are much more resistant to diet-induced weight gain, diabetes, and other cardiometabolic complications. Don't look at correcting the fat cell. You can't. It's out of your hands. You can correct the insulin.
We'll just dive right into fat, because this is maybe the most misunderstood, one of the most, let's say, misunderstood macronutrients. We call people macronutrients when they have excess adiposity. We call them fat, So let's actually define what fat cells, like the adipocyte, what are they, and maybe more importantly, what aren't they?
Mm-hmm. Yeah, that's a great way to get started. Unfortunately, because of our cultural aversion to everything fat, that has translated to an aversion to, or even a hatred of our fat cells. And the reality is they're not there by accident, and they're not there to hurt us. There are, in fact, diseases of people who have a genetic inability to make fat cells. And they are exceptionally lean. I mean, they are ripped, as you might say. I mean, they are incredibly lean, and they're incredibly sick. They end up getting fatty tissue, fatty liver, fat storage in their muscle and bones, and they develop all kinds of diseases. So that's my weird way of introducing the fact that fat cells are essential. We need them. But wouldn't you know it, nowadays they've gone too far. And so the fat cell is a cell that is on the surface designed to store energy. So if there's an excess and the body has been signaled to store energy, and those are not the same thing. So there's energy to store, and the fat cells are being told to store it, then the fat cells will store energy for later use. But beyond the simple metabolic aspect, which we both know is the one most people are interested in, is the fact that fat cells are also a very prominent part of the endocrine system within the body. They release a myriad of hormones that do all kinds of things for metabolically beneficial, and not only beneficial to metabolism, like regulating appetite, but also regulating things as fundamental as fertility and reproduction. People don't appreciate that aspect of the fat cell. So in my mind, the fat cell's been given a bad rap. And I say that as a fat cell scientist, but at the same time, of course, it is at the center of so many of the cardiometabolic and chronic disease problems that we suffer from today that we didn't suffer from in previous generations. These so-called plagues of prosperity really can be, if you drill down, you find the fat cell at the base of so many of these issues.
Yeah, and to reinforce that point that you made around sort of the importance of the fat cell, of course, someone like myself who's competed, let's say, in figure competitions, one of the things that we see when women actually reach a certain level of leanness is that they lose their period, or their menstrual cycle becomes very dysregulated. And so women are, and we'll talk a lot about kind of the differences between men and women, I'm sure, as our conversation progresses, but women sort of need a baseline higher level of fat in order to optimize our fertility. And I think that, in the battle of the bulge, let's say the plagues of prosperity, I really love that saying that you use. We do have to consider that there is, we can get too extreme with it. Certainly, we always think about like being over fat, let's say, but there is also some absolutely deleterious consequences of being under fat as well. So let's actually talk a little bit about some of the different types of fat, because I know that for a long time, you just mentioned it, that fat is part of the endocrine system. We used to look at them as kind of this like, inert, just like deposits and withdrawals, kind of energy storage system. But let's actually talk about some of the different categories of fat. And specifically, I'd love for you to delineate between white adipose tissue and brown adipose tissue, and what are the metabolic differences between those two?
Mm-hmm. Right. This has been an area of research in focus in my lab in recent years. So the body, there are numerous ways to differentiate fat tissue by location and by function. And it's the latter that we're addressing at this point, where we're talking about the functional differences between fat storage depots. And as you noted, we call one of these depots white adipose tissue, and the other we can call brown adipose tissue. It is, in fact, because of a difference in color. One of the things we do in my lab is do fat biopsies from humans from around their belly. And we'll take out a little piece of fat from the belly, and it is very whitish, a little yellowish. And it's because it is primarily just fat. In a fat cell, it is almost entirely made up of a big drop of fat, like a bubble of fat. And it looks a little bit like Crisco almost, not quite as pristine, or like coconut oil. Maybe I'll put it that way. So that is white fat. And it's white, again, because of the incredible amount of fat. You can't see that is in those fat cells, and you can't really see anything else about the cells. In contrast, brown adipose tissue has small drops of fat within its cell, but it also has a very high preponderance of mitochondria. In mitochondria, the so-called powerhouse of the cell that everyone remembers from biology, from high school biology, the mitochondria are in fact a reddish, kind of brownish, darkly complected color. And the fat tissue that is so enriched with those mitochondria reflects that tissue. I mean, it literally reflects the light, I should say. And so it looks much more kind of reddish brown. And that not only do we see that stark difference in appearance, I mean, it actually looks more in color like muscle in color than it does other fat tissue. But with that difference in appearance is a profound difference in metabolism. And this kind of reflects the fact that white adipose tissue does indeed store fat very well. It's no surprise that white fat cells have a very low metabolic rate. Of all the cell types we've tested in my lab measuring metabolic rate in tissues, fat has by far the lowest. And then when we measure the metabolic rate of the brown adipose tissue cells, they are about 10 times higher. Its metabolic rate's about 10 times higher. In fact, it's in the same range as muscle cells. And so that's a pretty substantial effect. Now, the difference goes even one step further, that not only do the brown adipocytes have a much higher metabolic rate, but then the question is, what for? And that might sound a little academic of a question. What for? What is the metabolic rate for? By that, I simply mean, what is the cell burning that energy for? Because a cell will normally burn energy based on what the cell needs. And for example, muscle and even fat tissue, the muscle or the fat cell will say to the mitochondria, hey, mitochondria, the cell, all of the cell, we need this much energy to do our job. Now, as I noted, muscle tissue has a much higher metabolic rate than white fat cells do. That's just because they're doing so much more. But regardless, the cell will tell the mitochondria, we need to do this much work. So give us this much energy. And that process is very coupled. That's what we call it. It's a very tightly coupled process. An analogy for this would be like someone who's driving a stick shift car and they're revving the gas, and they see the RPMs driving up, really revving up, but they're keeping their other foot on the clutch, or the car isn't in gear. And so the speedometer, the actual amount of movement in the car, is nothing. It's not matched. So the RPMs are revving, but the speed isn't moving at all. That's uncoupled. That's when we've teased the two processes apart. So the instance I was just talking about, we're revving the gas and we're moving at the same time. The car is in gear and it's going down the road. Now, as I mentioned, in the uncoupled state, which is what we have with the mitochondria in the brown tissue, that's basically when the cell isn't demanding work from the mitochondria. The mitochondria just keep burning energy. So we're revving the engine, but not because the cell needs any work done. It does, but its needs are adequately met. In this case, the mitochondria in the brown fat cells are uncoupled, as we say. And in this case, they are just burning nutrients. They're burning fat. They're burning glucose for no cellular work that the cell needs done. It's just to create heat. And heat is a chemical like waste. A biochemical waste. It is sort of the sign of a wasting of energy, back into the universe, if you will, or into the atmosphere. But in the human body, that does serve a purpose, particularly when we're babies. A newborn baby has a relatively high amount of brown fat. So of amidst all the chub on the baby is a relatively high amount of brown fat. And this is good because the newborn baby doesn't have enough muscle to shiver very well. And so it stays warm. If you lift your adorable little baby out of the bathtub, and he or she is going to stay warm, not by shivering, but by having all of this brown fat that suddenly turns on and starts chewing through nutrients just to create heat. Now, as we grow and our muscles grow and our body changes substantially, the relative amount of brown fat we have drops precipitously. And then much of the fat we continue to gain throughout our life is white fat. And that's okay. It works because if we're cold, we can shiver. However, we know that adult humans who have more brown fat or whose brown fat is more active, and we can talk about that, they are much more resistant to diet-induced weight gain and diabetes and other cardiometabolic complications. Now, on the human body, the white fat is basically the fat that you can pinch and jiggle. That's all of our subcutaneous fat and a little bit of fat within the abdominal space called visceral fat. And then humans have designed little pockets of brown fat kind of sprinkled throughout the thoracic cavity and up into the neck. Now that's not a lot, but my lab has found that when the white fat cells start consuming ketones as an energy source, they will actually enhance their mitochondria number, and the mitochondria will be more uncoupled. So we found in humans that when humans were in ketosis, their fat cell metabolic rate went up by 3 times. Now, that didn't get up to the 10 times higher that you see with brown fat, but still a tripling of the metabolic rate of fat cells is nothing to sneeze at. And this might be why people
of the white,
in ketosis,
sorry to interrupt you, but of the white adipose tissue? So
that's right. That's exactly right.
Okay.
Yeah. So that's a process that is referred to as beiging. So it's like the white fat cell hasn't fully become a brown fat cell. It hasn't, and it can't, but it's started to act a little bit like those brown fat cells. So it's not quite brown, but it's not quite white anymore. It's beige. And so we say that it was a beiging effect. So we found that the ketones have a beiging effect on the white fat, increasing their mitochondrial content and making the mitochondria behave in a more uncoupled state. Now, it's no surprise to people to learn that cold immersion will do the same thing, but that's, of course, a much less pleasant phenomenon by many standards than just being in ketosis through fasting or dietary control. But nevertheless, it does touch on the fact that you can leverage this biochemical phenomenon to have your fat cells start to really work in your favor in order to facilitate weight loss. So ironically, the fat cell begins eating its own fat as its metabolic rate has climbed, further facilitating fat loss. So that's really the maybe deeper than I intended to get, the differences between white fat and brown fat. They're very substantial differences, and we can kind of take advantage of that through lifestyle intervention.
No, that's perfect. That's even more like all the detail, all the nerds that are listening to this, all are just like frothing at the mouth right now.
Yeah,
so
good.
That's great.
Good.
Yeah. So 2 questions come up for me when you're talking about this. So you said that the white adipose tissue, when there's in the presence of ketones, can increase their mitochondrial density, which is going to lead to that mitochondrial uncoupling, which is like that wasteful, even though it's like advantageous, like that beiging effect where we're creating more heat. So is it ketones that are endogenously produced, where it's like you're in a ketogenic diet or you're fasting? Or do we also see that with exogenous supplementation as well? And then my second question is, does that suggest then that this beiging effect, like does the beige ever get to brown? Like can we actually convert white adipose tissue to brown adipose tissue through interventions like plunging in a cold, I see people all the time, they have these big cold plunges, everything's filled with ice, or, fasting, or some of the lifestyle recommendations that you mentioned.
Yeah. Great question. So my work touched only on endogenous ketone production. Now, I would strongly suspect that it wouldn't matter. That ultimately, what ends up coming to the fat cell that matters is the ketone, and whether it's an exogenous ketone or endogenously produced through massive fat burning when insulin is low, it is the same molecule. I mean, that is the value of the exogenous ketones. By the time it gets to the cells, it's become the same molecule as if the liver were making it. So I can definitely speak to the endogenous aspect, but I am speculating that the exogenous would be no different. Now, I don't mean to sound like I'm some table-pounding advocate of exogenous ketones. I think that they can absolutely play a role in someone improving their metabolic health, but I don't ever want to appear as though I'm some advocate for them. And then with regards to the degree to which the white fat can change its fate and become brown fat, I know of no evidence to suggest that it can ever go all the way. I don't believe that could be possible. It would take a remarkable series of events and very likely nothing that the body could do on its own. Maybe someday some drug interventions or some injectable treatments. But I would actually think some interventions that would actually make the conversion possible from white fat to brown fat. But wouldn't, as the kind of cell biologist, fat scientist, there's a part of me that would think, oh yeah, that would be great to control obesity, but it would be catastrophic to things like appetite control and fertility, because brown fat cells do not behave in the same endocrine fashion as white fat cells. Like, for example, we've touched on a little bit fertility. Leptin, while we always think of leptin as only regulating appetite, it is utterly and totally essential to fertility. That's why if someone has a leptin deficiency, they are infertile. They're sterile. They cannot reproduce. You have to give them leptin in order for them to have a normal fertility capability. But brown fat cells produce essentially no leptin. And so it would be in a way catastrophic to the species, if we had people who were suddenly shifting over, not only catastrophic to the species, no reproduction, but even to their own health. Especially a woman whose body thrives on the remarkably dynamic cycling of the hormones that swing around so remarkably during a menstrual and ovulatory cycle. That would basically all be stopped in the absence of leptin. And that would be very bad for bone health, very bad for mental, emotional health. Now, I know I'm not a woman. I sometimes get a lot of heat that people suppose I can't talk about it. I'm an endocrine expert. I teach graduate level endocrinology courses, and I'm a fat cell scientist. So there are some things I can speak to as an authority, not because I'm a woman, but because I know hormones. So white fat.
I just have to stop for 1 second. So this is maybe this is like the issue with our society encapsulated in just a single statement. If you are a fat cell scientist, certainly you can comment irrespective of your sex, your chromosomal sex.
I would think so too.
Let's stop. Okay.
I know.
Okay,
I know.
Believe
me, Stephanie.
You're not mansplaining. You're not mansplaining anything. Okay.
Like
you're speaking from a point of science and education, and I think empowerment. So let's Anyway,
good.
Yes.
Okay. No, good. Yeah. I knew I was in good graces with you, but I'm amazed at the number of people who basically, as an aside, we live in a culture where people just are so eager to be offended, right?
Sure. Yeah.
They're just looking for any opportunity. Well, don't take an opportunity here. So yeah, as much as it would sound like it's a good thing, let's kind of go all the way. Not that either of us is suggesting it. There would absolutely be consequences and they wouldn't be good. I think that the sweet spot is through fasting and optimized lifestyle habits, you can sort of push the fat cell a little bit that direction, and you just get a little bit of that advantage, the metabolic advantage, without losing the fundamental necessity of the white fat in the first place.
So you can get a beiging, but it's never going to turn fully into like a brown adipose tissue. Okay. So we talked about the different functions between white adipose, brown adipose tissue. You mentioned briefly location, and you mentioned, let's say with white adipose tissue, maybe we find that more in the belly. For females, I would say under the influence of estrogen and maybe more specifically estradiol, you're going to have more especially when she's in her kind of fertile years and she's in her reproductive years, let's say, we're going to see more fat deposition through the belly, kind of through the hips, the bum, the thigh area. Is that primarily white adipose tissue? And you mentioned like the brown adipose tissue is primarily in the cavity. Are there any other, in the chest cavity rather, is there any other areas that we missed in terms of where we might find BAT?
Yeah, wonderful question. So I'll start with that last question first. No, brown adipose tissue is it is completely mingled through the ribs, then up into the clavicular space and up into the neck just a bit. It's an odd location, right? And it's certainly not something you can look at and say, well, gosh, my brown fat sure is getting big. You wouldn't see it because it's so enmeshed within the cavity itself. My speculation is that we have brown fat there in order to ensure all of the blood that's going to be coming up into the brain is warm in the event that the body is very cold. That if we're cold everywhere else, like you're immersed in an ice bath, you can shiver because you have muscles everywhere from your neck down. Well, we have no muscles up in our head. There's no muscles to shiver to keep the brain warm. And so we have these little incubators around all of these blood vessels coming up, particularly the carotid vessels. And we can warm all of the blood up before it gets to the brain. That is admittedly a little speculation, but I'm confident in it. And then to your first point, sex hormones determine, let me rephrase that. Sex hormones largely determine where a person stores their fat. And when you look at a little boy and a little girl who are growing up, they look identical in their body shape. There's no difference until they reach puberty. And then the moment the sex hormones come into play, the sex hormones, among the many effects they're having, metabolically speaking, determine where the body will store fat. They're literally, like estradiol is literally enhancing the expression of enzymes that will dictate fat storage at breasts, hips, and buttocks, the kind of prototypical female sites. Whereas the androgens are largely inert. They don't really promote fat storage anywhere, but the only hint of it is centrally, abdominal. Now, all of that is white adipose tissue. Anything you can pin, and that is particularly true in females, because females relatively store so much more of their fat as subcutaneous fat than males do. Part of the androgen effect of fat storage is a little more visceral fat. So that's the fat that is enmeshed around the organs behind the muscle of the stomach. But the estrogen's effect on fat storage is overwhelmingly subcutaneous. And that's good because, one, subcutaneous fat produces more leptin than visceral fat does. And two, if you have a woman who's storing a lot of fat viscerally, especially during her reproductive years, it may complicate the fact that you're about to grow a baby there. And now that the fetus is in the growing uterus is competing for very limited space with all of that visceral fat tissue. The visceral fat would be like actually pressing in on that very area. And so it's no surprise to me that the female phenotype is designed more to store fat subcutaneously because it gets the fat out of the way of that critical area on her body for fertility. Now, you'd mentioned very early on, and I was struck by the comment, and I just wanted to come back to it, that women do naturally have a higher set point for adipose tissue. It is supposed to be that way. Part of it is the necessity for leptin. Women's female fertility is much more dependent on a higher amount of leptin than male fertility is. And I believe, here's a little more speculation, but it's informed, that that reflects the fact that the female body bears the metabolic burden of fertility. The male has a brief, wonderful moment, and then his role in essential role in fertility is over. Now, I would submit that the dad has a profound role through the life of the child, of course, but even still, the burden, if you will, and I don't want to use that term. That term may be too loaded because, having had a wife who was pregnant multiple times and we have beautiful children, it's also incredible, but it is a burden on her body, a metabolic burden.
It's physically and chemically demanding.
Yeah,
absolutely.
yeah, good.
Yeah.
Right. Yeah, you said it. That's right. So her body carries that metabolic burden. And basically, my thought is that her brain needs to know that there's enough fat on her body to carry that baby, to develop that baby, to gestate that baby, because her metabolic rate will be higher during pregnancy than it has been at any other point in her entire life, because she is working so hard to grow her own tissue and to give the energy to the baby to grow the baby. And then even when baby's born during lactation, her metabolic rate stays very, very high because she's still producing enough energy for two. So it's basically the brain's way of saying, hey, fat cells, is there enough of you that if we suddenly had reduced access to food, you have a lot of fat on you and we can carry this baby. Now that I don't, mean to assume like starvation, that would of course be a big problem, but it's basically the brain's way of ensuring there's enough stored fat that it is okay allowing fertility to move forward. and that is through leptin. If there's enough fat cells, there's enough leptin going to the brain, and the brain will turn on this gonadotropin pathway, going to the pituitary, then going down to the ovaries and telling everything that it can go forward. If there's not enough fat cells, there's not enough leptin, then the brain will shut that pathway off. It will turn off that axis of that gonadotropin releasing hormone from the hypothalamus, and then everything downstream of it. The pituitary will turn off its follicle stimulating hormone and luteinizing hormone, and the ovaries will just reduce all of those sex hormones. And then fertility would stop, ovulation would stop. So there's so much nuance here, isn't it? And the female fertility cycle is just so remarkably complicated. I like to joke that male fertility is like a barbershop quartet, and then female fertility is like an orchestra. That reflects the fact that her body bears the metabolic burden, not only of the gestation, but also of the lactation and feeding the baby. And so it's no surprise that it's a very, very complicated affair. But all of it, even still, comes back down to the humble and often misaligned fat cells.
And this explains in part, you're talking about kind of coming back to location, like the morphology, let's say, of a woman in her reproductive years, we'll use fruit, like kind of like a pear, right? So sort of bottom heavy, right? For this this advantage, let's say, should she become pregnant, that we don't have this visceral fat in the way of, the baby. And even if you've ever looked at, almost a full term, woman who's in her third trimester, like the liver and like everything literally moves out of the way for this baby. It's actually quite remarkable. But it also explains, as a woman moves out of her reproductive years and into, let's say, menopause, where now we have this very acute drop in her estrogens, estradiol in particular, as we've been talking about, and maybe she loses that, let's say, aromatase activity, and she becomes potentially a bit more androgen dominant. Why we tend to see a lot of women in their menopausal years, they have that ectopic fat distribution where they tend to put weight kind of more centrally. You sort of said, the androgynous type is to sort of put fat or deposit fat more centrally, kind of in the, like that visceral fat. So thinking about sort of the arc, let's say, of a woman's life, where we see her, you mentioned in pregnancy, she has this increased metabolic rate. In her fertile years, I'd actually like to, maybe we'll come back to the fertile years for a minute, and then we'll come back to menopause. Can you speak to, over the course of a woman's cycle, and this relates back to fat because I want to get into a conversation around insulin resistance and insulin sensitivity with you, how her, under the influence of some of these metabolic hormones, you've mentioned leptin. I'd like to bring insulin into the mix if we can. How that sensitivity, let's say, oscillates over the course of her menstrual cycle, and then how that changes when she moves into menopause.
Yeah. I'm thrilled you're bringing this up because it's such a fun topic to kind of explore the dynamic nature of metabolism and insulin resistance. So yeah, people will have heard me talk about insulin resistance in our first episode together. So I'm not going to redefine it, but I will just revisit it briefly by saying insulin resistance has two aspects of itself. One is the pathological side, which is the version of insulin resistance which promotes chronic disease, these so-called plagues of prosperity, Alzheimer's disease, fatty liver disease, hypertension, heart disease. All of those are consequences of insulin resistance and the pathological version of it. But there is a physiological side of insulin resistance, which is when the body becomes acutely insulin resistant to serve a specific purpose. And that is the insulin resistance that we're touching on now when we talk about the changes, particularly during the menstrual cycle. So a woman will become relatively a little more insulin resistant during the actual menstruation. Like right after, progesterone has come up, well, I should say it's kind of right before. It's right before, right as the endometrium is kind of at its thickest and progesterone is peaking. Then she is at her peak insulin resistance during that cycle. Now, it does not get to the point of like clinically, problematic. But if her insulin resistance were humming along throughout the month at a very, very low level, or let me say it another way, she's very insulin sensitive throughout the entire cycle. And then with those few days, right around the time of ovulation and progesterone has come up, then she becomes a little insulin resistant. And then as she starts to shed, there's no implantation, no fertilization, then things go right back to insulin sensitive. But that's because progesterone is a hormone unlike estrogens. The estrogens, how can I say this best as I start weaving in these numerous topics? I'll try it this way. The estrogens tell the body where to store fat, but not how much fat. That's very, very important. Overall, estrogen actually has a fat burning effect. This is why at any moment in time, a woman is burning 40%, relatively 40% more fat than a man is. Now, a man has a higher metabolic rate just because he's bigger, but a woman, relative to her body weight, will be burning 40% more of her energy from fat. And that is very, very heavily dependent on the estrogens. So estrogens tell her where to store fat, but also tell the body to rely on that fat. So a lot of fat is going into those fat cells, but a lot of it's coming out to be burned. So there's a high turnover. That's a very healthy way to store fat. Progesterone tells the body to store fat, and it does so by leveraging insulin. And so during that period of time, progesterone promotes a slightly insulin resistant body, and that means insulin levels have to come up a little higher to overcome this subtle insulin resistance, throughout the entire body. But that doesn't happen at the fat cells. The fat cells do not become insulin resistant. And so now this higher than normal insulin promotes a slightly greater than normal fat storage. So hormones like progesterone and insulin tell the body how much fat to store, whereas the sex hormones, well, progesterone's a sex hormone, so the estrogens and androgens tell the body where to store fat. And those are not the same thing, of course. So there is that acute little moment of insulin resistance, nothing to be concerned with during that moment of the month. And then after that, after her fertile years have passed her by, and as you noted, at that point, the aromatase expression changes in the ovaries, and her estrogens production starts to drop a lot. At that point, she's lost that kind of fat-friendly and even protective effect of the estrogens, and now she's sort of subject to the whims of the androgens a little more with regards to fat storage. Now, this is not to say her androgen levels go up really high. No. They don't change that much. It's just that the estrogens.
It's the relative amount.
That's right.
Relative amount. Yeah.
Perfect. That's perfectly right. And so now her body just starts to store fat in more of an androgenic way. In other words, as you perfectly mentioned a moment ago, more centrally. And she can literally start to lose some of that fat that she had been storing on her breasts, hips, and buttocks, because the estrogens were what was determining where that fat should be stored. And that then starts to, in a way, that at that point, the woman starts to lose the metabolic protection that the estrogens had provided her. Estrogens, in a way, provide a metabolic protection for a woman, allowing her to basically avoid the consequences of her fat tissue, the metabolic negative consequences. She's been protected from it. Estrogens help her body know what to do with fat and handle the fat in a good way. With the loss of those estrogens during menopause, now she's no more protected from the fat than her male counterpart is. Her risk of disease from fat tissue starts to match that in the males. So I like to joke that that's when the woman loses her metabolic superpowers and becomes a mere mortal like the rest of us men are.
And that's actually why we see things like, you're talking about like like when we look at the onset, let's say, of cardiovascular disease, which you can argue is a disease of fat and lifestyle, let's say, we see this phasic shift where men will sort of reach the point of inflection or no return, maybe is a way to say it, earlier than women, but just the same amount of women reach it. It's just like, let's say 10 to 15 years later. And it usually that increase in risk starts at the point of menopause, to your point, where the estrogen, like that estrogenic protective effect, let's say, is now gone. And now she's a bit more maybe androgenic, potentially, a bit more. Her body behaves, and this is not to be meant in a derogatory way, but it behaves more male, which also means, like, we're going to get to actionable items in a moment, but it also means that she can start to behave in some of the tools and applications. We don't have to be as stringent around fertility and worrying about the impact on the oocyte and the mitochondria. Like, she can actually have more aggressive fasting. She can actually do a ketogenic diet for a longer period of time, let's say. Whereas for a woman who's in her fertile years, one of the things that I wrote about in my book, I know that it's reflected in your book, Why We Get Sick, is that women who are in their reproductive years do have to change the way that they eat and to a great, and I would also say train, when they're exercising differently through the cycle to match some of these metabolic, or I'll say these ever-changing metabolic environments as well. I had a question for you. I just wanted to come back to estrogen and progesterone because I was making notes as you were talking. So estrogen tells the fat where to go. Progesterone says how much, and it does so by leveraging insulin. And you said that women are burning 40% more fat than our male counterparts are. Does that have anything to do with the increase? Like, women typically have a higher percentage of type 1 muscle fibers, which tend to be more we'll say fat burning, let's say, than they are glycolytic. Is that play into the mix as well, or? That's
a really good point, actually. That might be part of the demand for that fat from the fat cell, but you can actually, this goes right to the level of the fat cell. If you were to take a fat biopsy from a woman and a fat biopsy from a man, and if you were able to put those fat biopsy tissue, the fat tissue, in a little beaker in a science lab and keep the tissue alive and active, it would literally be secreting 40% more of its fat at any moment than the fat cells from the male, from that same location. You pop it out of the belly. So you invoking the muscle, that could be part of the demand. In other words, the pull, where there could be a differential expression from the female muscle cells. I don't know this, so I'm speculating, but muscle tissue releases a myriad of hormones as well. And it could be that that there's a difference in expression of hormones hormones like FGF21, for example. That is a muscle-derived hormone that can activate lipolysis. I don't know about that. I can't speak to it, but I do know that the estrogen effects simply enhance lipolysis on their own. So we can remove the muscle from the equation, although in the whole body we can't, and I believe it's very likely relevant. But just sticking with the sex hormones and the fat cell, estrogens simply activate lipolysis at a higher rate, especially at subcutaneous fat cells. And the differences go even further. The estrogens not only tell the body where to store fat, but also how to store it. One of the reasons females can store more fat than males pre-menopause and be much, much healthier is that the very nature of her fat cells is different because of the estrogens. Estrogens, specifically, particularly at the buttocks and hips, much to the woman's dismay perhaps, provide an almost limitless phenomenon of hyperplasia. So anytime the insulin or the progesterone is telling her body to store more fat, because they control how much fat the body stores, the estrogens will tell those tissues, buttocks, the fat tissue in the buttocks and hips, hey, the moment the fat cell gets a little big, just recruit another fat cell and recruit another fat cell and another fat cell. So she continues to store her fat there by making new fat cells. That might sound like a problem, and it might be a problem if she's trying to squeeze into her college jeans that she used to wear. But metabolically speaking, it's magic, because when fat tissue is growing through hyperplasia, the fat cells stay small and they stay very metabolically healthy. In men who have relatively much lower levels of estrogens, there is none of this hyperplastic stimulus. And so his fat cells, if there is a pressure to grow, not through progesterone, of course, exclusively through insulin, they almost totally grow through a process of hypertrophy. And the fatter the fat cell gets, the sicker it gets and begins to promote insulin resistance throughout the body. So the protective effects of the estrogens go through multiple levels here, not only burning fat at a higher rate at any moment, but also altering the very nature of how she stores fat at those locations particularly. But again, this plays into part of the pathology, if you will, of menopause, where she loses that another protective effect. So not only is she losing the protective location, the storage in the subcutaneous depot, relatively shifting to store more viscerally. But then as she is storing more fat, her fat cell number starts to go down. But again, that's not a great thing, because that does mean, in the absence of any other changes, and Stephanie, you mentioned it very, very well, to me, there's an opportunity there for lifestyle change. But as she starts to lose her fat cell number, if she continues to eat the same way and live the same life, then her body still wants to store that fat. It just has to store the fat now in fewer fat cells, inducing a greater and greater hypertrophy, and perhaps storing the fat in tissues not designed for long-term fat storage, like the liver and the muscle, etc. So she loses multiple protective benefits. Again, that all plays into why I say estrogen allows the woman to be a metabolic superhero. And with the loss of that estrogen, she just becomes a mere mortal.
So we have, hyperplasia, just in case my Betty's your lost. So hyperplasia is more fat cells. This is under the influence of estrogen, let's say. Mm-hmm. But this is as you were saying, like much to her demise, more fat cells, maybe not so great for the bikini, but it helps her stay metabolically healthy. When we transition to, let's say, a lower estrogen environment, like peri or menopause, then we don't have that ability to keep the fat cells small anymore. We have the same kind of, we're a bit more set in the number, but the individual fat cells are becoming trophic. They're becoming bigger and bigger and bigger. And that's when we can get, and maybe you can touch a little bit on like the fat cell, like that adipocyte now is starting to get like really, really big and inflamed. It's going to start leaking, let's say, pro-inflammatory cytokines, and the ceramides and like all the things that you talk about in your book, where then we see this like pathology of inflammation, like this like creep that happens at menopause.
Yeah. Oh man, gosh, you've become a master. You're invoking all the right ideas here. Yeah. So when the fat cell gets too big, we almost have to feel bad for it, because it starts to try to survive. But the two ways that I'll mention in a moment in which that it leverages in order to survive end up, unfortunately, creating metabolic havoc for the rest of the body. So the two things, you mentioned the inflammatory cytokines, so let's start there. When the fat cells are hypertrophying too much, they begin to actually push each other further and further away from capillaries, blood vessels. And the capillary is the site of exchange for a cell. It's where it gets new oxygen. It's where it dumps off its CO2 from its metabolism. It's where it receives new nutrients or gives out its nutrients. And so suffice it to say, a cell has to be very, very close to a capillary in order for that to work. But as the cells are hypertrophying so much, now it used to have maybe a micron or two away from a capillary. Now it's getting several. It's increasing multiples in distance. That is catastrophic. It will literally die. It will suffocate. And it will undergo a process called necrosis. It will rot and die. And we don't want that. So the hypertrophic fat cell, who senses that it's becoming increasingly hypoxic or reduced in oxygen access, it will start to secrete pro-inflammatory cytokines, because some of those cytokines will induce the production of new blood vessels. So this is the big fat cell's way of saying, hey, capillary, you're too far now. I'm sending you this message. Bud off, branch off a little capillary to come out this way so that I can start to get some blood so that I don't die. Now, that helps the hypertrophic fat cell survive, but at the same time, it's secreted a whole panel of pro-inflammatory proteins, only some of which, largely one, is actually helping with the improved blood flow. but it just sort of belches them all out. And then it's all the rest of these pro-inflammatory cytokines that begin to promote a subtle but relevant inflammation throughout the entire body. Like the body is fighting a mild infection in the absence of any actual infectious agent. It's just this fat cell doesn't know what else to do. At the same time, the fat cell is reaching a point of maximum dimension. And I know of no comparable effect where you can take a normal sized fat cell and in the presence of insulin to promote its growth, it can grow to 10 times its volume. And unlike any other phenomenon in the body, where it will grow 10 times. And at that point, it begins to reach a point of maximum dimension where it simply starts to tell itself, I can't grow anymore, or I will overwhelm the ability of the cell membrane to hold us all together, and we will literally burst apart. And so the hypertrophic fat cell starts to tell insulin, you want me to keep growing. And so while I can't stop you from shoving the nutrients in, because it can't really, I can stop you from preventing me from breaking down my fat and leaking out my fatty acids. So that's what happens. I know I got that a little complicated with a bunch of double negatives, but basically insulin would tell the fat cell, don't break down any fat. In other words, inhibit lipolysis. Lipolysis is the technical term for breaking down stored fat. But the hypertrophic fat cell says to insulin, I can't stay this big. I can't continue to grow like you want me to. So fat keeps coming in, but now the hypertrophic fat cell starts letting fat out. And so we have two phenomena occurring in the body overall because of the hypertrophic fat cell. One, the body's becoming ever more inflamed. And two, the body's becoming filled with circulating fat that it doesn't know what to do with. Those free fatty acids that it can't burn because insulin's too high. And if insulin's high, the body doesn't burn fat. It can't really store in the fat cells anymore because the fat cells are already too full. And so then you have this more ectopic fat deposition that we've both alluded to already, where you start storing fat in tissues that are poorly designed for fat storage, creating things like fatty liver disease, and that could progress into full-on steatohepatitis and cirrhosis and liver failure and myriad other problems. But it all comes back to this series of events, a fat cell that has become overfull, or in other words, hypertrophic. And then to bring that back to the female phenotype, it starts to happen with the loss of estrogens.
And is there a way to make those hypertrophic fat cells insulin resistant? Meaning, is there a way for that cell that's like growing and growing, is there a way to downregulate its sensitivity to the effects of insulin?
Yeah, it's not, no. In fact, you can't. That's a really, really good question. You can't do that. And I would submit you wouldn't want to. So what you would want to do, rather than just correcting the fat cell's ability to respond to insulin, what you'd want to do is allow it to respond well to insulin. And while you cannot control the effect of the fat cell, you can control the insulin. So don't look at correcting the fat cell. You can't. It's out of your hands. You can correct the insulin. And that comes back to all the strategies we've talked about before, and I know you've talked about in other podcasts. So we can't blame the fat cell for just doing its job, and so we shouldn't try to correct it. What we should try to correct is the stimulus that continues to aggravate the fat cell, because that we can correct.
Okay, so let's talk a little bit about that. Let's talk about, and maybe we can do this through a metabolic lens. So we've been talking about insulin. Let's talk a little bit about glucagon, because the insulin to glucagon ratio, let's say, I think is important. And then I think it also leads into some of these actionable items. We've been kind of dancing around it, but I definitely want to have a deeper dive into like some of the things we can do at like protein intake. And I think that protein intake, let's say the state that you're in is, whether you are, let's say if your insulin levels are high or your glucagon levels are high, I think that also is going to, let's say, determine the fate of what happens to that protein. So can we talk a little bit about glucagon? I don't know if we talked about this last time, but maybe just like a quick review, what glucagon is, what does it want us to be doing? And then let's talk about how that might relate to protein intake as well.
Yeah, that's a really, really great question. And it's a big one, too. For the sake of time, I won't answer it in too much depth, but I would say that I've spoken about this and I actually have a talk on YouTube. So anyone who wants to go a little deeper, just go look for Bikman and glucagon and protein. But glucagon, as we invoke a new hormone in the conversation, in our conversation now, glucagon is insulin's opposite, the yang to the yin, and that is reflected in multiple cellular processes. The most obvious is their battling effect with glucose, whereas insulin wants to lower glucose at any moment of time. Glucagon wants to increase it. But the differences continue. And it's in a way thematically represented by the fact that insulin wants to store energy in the body. Glucagon wants to burn it. And this is also reflected in ketogenesis, the production of ketones.
She's got a credit card. Glucone has a credit card, and she wants to go shopping. She
well
wants
said.
To use the fat use, create liver glycogen. Yeah, exactly.
So that's perfect metaphor. But as I noted, ketogenesis is the process of burning a lot of fat and turning it into ketones. Well, it's no surprise that insulin inhibits that, because insulin doesn't like burning things. It just wants to store them. And it's no surprise to learn that glucagon activates that. It stimulates it. So it's the balance of these two hormones that, in a way, have a profound whole body effect on nutrient metabolism. And now you mentioned protein. It's interesting to note what protein does. I'm an enormous advocate of dietary protein. I think most people don't get enough of it, and they're accidentally avoiding the best sources of it, or deliberately avoiding the best sources of protein. But protein will have a variable effect on insulin and glucagon. If someone has very, very high glucose levels, then protein can have, in fact, an not inconsequential effect on increasing insulin. So if you have protein in the midst of high glucose, it can be pretty significantly insulinogenic. And then this overall ratio of insulin to glucagon gets quite skewed. However, if the protein is being consumed with fat, as it is in nature, there is literally no exception to this. In nature, all protein comes with fat. Always. In our hubris and our fear of fat, we've pulled the two apart, thinking we know better than nature does. So I'll just talk about protein alone. But if the protein is coming into the body in the absence of a high glucose level in the blood, then the insulin effect is essentially non-existent. It may be there, but it's very, very modest. And this has actually played out in multiple human studies. I very much resent people saying that protein has a significant insulin effect, because I can disprove that so readily through so many human studies. It doesn't in the absence of glucose or in a normal glucose level, but it does increase glucagon. And so overall, the net metabolic effect of the protein is metabolically favorable, in that it is going to help the body use energy rather than just store it. Not to mention the fact that protein has a very good effect on satiety, and protein increases metabolic rate because of the act of digesting and absorbing it more than the other nutrients do. So for all of those reasons and more, I'm an advocate of protein, but that even is reflected in these hormones like insulin and glucagon, and others like ghrelin that would stimulate hunger that goes down, and other hormones like GLP-1. But suffice it to say, I'm an advocate of protein. I know you are too. And the overall, the net effect on the metabolic state of the body is reflected in a way with the changes in insulin to glucagon in their ratio.
So if you're eating a lower carbohydrate diet, let's say, so maybe it's ketogenic, or maybe it's just like low carb-ish, right? Mm-hmm. It's like paleo-ish, let's say, where you might see a prolonged clamping down, or your insulin levels are low. We might assume then that glucagon is higher, and then we ingest protein at that point. It's unlikely that we're going to see like a massive insulinergic spike. Whereas if you are kind of hyperinsulinemic, right, where your insulin levels are high, and that might you might conclude that then, your glucose or your carbohydrate consumption is higher. Following kind of this line of thinking, then protein then with the presence of glucose might have a kind of insulin spiking effect, where it might then trigger things like gluconeogenesis and all of these sort of undesirables, let's say. Is that correct?
Yeah, that's right. Yeah, we would say that's perfectly stated. We would call it undesirable in the midst of someone who's kind of overweight and insulin resistant.
Yes.
And I think that's apt. I would say that too. But it's interesting for me to think about nature and the working of the complexity of the human body. It's interesting for me to note that I am, to my knowledge, the only instance where protein comes with glucose or a carbohydrate source is dairy. And in fact, dairy, as mommy mammal is producing this perfect food for baby mammal, it is high in all three macronutrients. It's high in fats and proteins and lactose, or what becomes glucose. And I look at that and think, what a perfect formula to stimulate as rapid growth as possible. And so if there is an insulin effect from that protein and that lactose, which there would be, there certainly is, then all the better, because it's going to help that baby grow. And it will help that baby have adequate fat tissue, which that baby desperately needs in order to make ketones for its brain growth. Not to go on a tangent like that, but a newborn baby will get into deeper ketosis after 2 or 3 hours of not eating than an adult will in 2 or 3 days. A baby is in a massively fat-burning ketotic state. And the thought of the reason for that is very likely because ketones are such a profoundly beneficial fuel for the brain. And this is why a baby that is born underweight may develop learning disabilities later because of, in fact, a little stunted brain growth. You need those fats and those ketones to adequately fuel the brain. There's a whole area of research on this, which I can only lightly speak to, but I'd encourage anyone to look up a book by the work by a scientist who's up in Quebec, actually, named Stephen Cunnane. And his book is called Survival of the Fattest, which I love. But it is brilliant work. And he sort of posits an alternative theory of human evolution. Of course, it's all a theory. All of evolution is a theory, after all. But it's very, very compelling. And it really puts fat tissue in a primary position. And of course, he backs it up with very significant data. But anyone who's interested to learn more, please look up Stephen Cunnane's work. It's just fantastically interesting. But nevertheless, back to the baby and dairy and protein and glucose. I believe that's the only source of protein in nature that comes with a high carbohydrate load as well. And I don't think it's an accident that it happens to be the one food that is specifically designed to help a human or any animal grow as quickly as possible.
And so you mentioned ideal sources of protein. What would be, in your opinion, because there are, and this is not to, get into, we'll say, dogma, because there can be sort of some dogma around this, but what are some of the ideal sources of protein in your professional opinion?
Yeah. So my professional opinion will only rely on peer-reviewed studies in humans, and the best sources of the best sources of protein, the best source of human is
right here. This is the best source of humans right here.
Best source of protein is any animal source protein. Now, I know this starts to touch on very culturally sensitive ideas, and I'm certainly sensitive to those. I truly am. I hope I never am too flippant or irreverent talking about people's kind of ethics and morals. Even if I disagree with them even profoundly, I still want to be respectful. But the fact is, every animal source protein has a higher digestibility and absorption and better amino acid profile than any plant-sourced protein. That's just reality. And I can just speak to that. And that's also, I think, reflected in nature. Throughout all of human existence, we would have gotten our proteins from animal sources. Thank goodness. And indeed, Stephen Cunnane's work touches on this. And so do other evolutionary biologists from Harvard who posited many, many years ago a theory called the expensive tissue hypothesis of human evolution, which basically stated that humans deviated from other primates because they started eating high-fat animal foods. And that is unlike other primates. Most other primates primarily subsist on plant matter. And that allowed the human body to change in two very, very meaningful ways. By eating very high nutrient-dense foods, which all animal foods are, by orders of magnitude more nutrient dense than any plant foods, it allowed the intestines to get significantly shorter. And indeed, our intestines are significantly shorter, especially our large intestine, compared to any other primate, because we didn't have to ferment stuff. It just, everything we ate was so immediately digestible and absorbable that we could shrink everything, especially the large intestine. We didn't need it anymore, basically. And at the same time, because we were eating such nutrient dense foods, we allowed our brain to get significantly bigger. So again, that's what's called the expensive tissue hypothesis. Again, another theory of evolution. They all are, but this is just undeniable. Humans are built, we are designed to eat animal-sourced foods. Now, again, people may have their own reasons for avoiding them, and I can't speak to that, but it cannot be due to a hope to be healthier and stronger, because the further a human gets from animal-sourced foods, the more nutrient deficient they will start to become. And so they need to, so something like veganism requires not only a high level of education to be aware of the nutrients that you will be deficient in, because you will be. That's just a reality. I don't mean to speak evil of that paradigm of eating, but you will be deficient in nutrients, so you have to know what those are, and you have to just make sure you can afford the good supplements, the high-quality supplements, to make up for those deficiencies.
Yeah, I'm so glad that we've touched on this, because I think that more women, at least in my observation, I could be wrong here, but more women tend to be attracted to and try the vegan diet. So what often happens, and I would actually say this is true for the ketogenic diet for women as well, but like you start this new intervention, right? So maybe it's vegetarianism or veganism. And they feel initially a lot better, right? Like they start eating more plants and they have more energy and their skin clears up and all the things. And it's probably a proxy of eating more plants than they were prior. But then, you sort of ride that sort of maximal benefit, like that area under the curve, and you sort of get to the other side of the curve, and then the hair starts falling out, and, their energy tanks, and, some of the initial complaints around why they maybe, from a dietary perspective, like forget the ethics and the environmental argument for a moment, they start to experience maybe some deleterious effects from the diet. And then what ends up happening, at least in my observation, is a lot of women will say, gosh, like I just got to do this diet harder. Like I just got to be as strict as I was when I first started, right? Rather than maybe saying, okay, maybe I've actually ridden the maximal benefit curve of this diet now. That metabolic intervention of having more plants has kind of served its purpose. Maybe I need to reintroduce some animal proteins and become the omnivore, and kind of in line with that, that teleologic or that evolutionary lens that you just provided. And what I so often see in terms of nutrient deficiencies, it's like the B vitamins are not there. We have, and they're not able to, to be a vegan. I think you need to be very, you almost have to be a chemist, because you have to know what foods to combine, because you're not getting the full complement of like amino acids, let's say, because plant-based protein sources are incomplete by nature. And as you said, they're not as bioavailable. And in order to kind of trigger, we've been talking about protein, and I like to talk about protein in the context of body composition, in terms of maintaining muscle mass and bone mass, there needs to be sort of like a minimum amount of leucine, one of the amino acids that we consume, in order to drive muscle protein synthesis. And you don't really get that in the equivalent. Like if you take a scoop of, I know we're just talking only protein right now, which, to your point, doesn't occur other than a whey protein powder, right? But if you take like a scoop of whey protein, right, versus like pea protein, like scoop for scoop, you're going to have to consume, I remember doing the math on this for my book, it was like around 25 to 40% more of the plant protein compared to the animal-based protein. So then for those women that are like, okay, I'm trying to lose weight, now you're consuming 25 to 40% more calories, right? So now this also gets thrown into the metabolic mix, where you are constantly needing to overconsume calories in order to get that minimum viable kind of protein, that MVP, maybe, if you will, in order to kind of drive that MPS, that muscle protein synthesis.
And I would add, before we move on, the problem with many of these plant proteins as well is that as you concentrate the peas, for example, to get the protein from them, it's those amino acids that you want to get. But as you concentrate those peas to such a high level, because peas are so deficient in amino acids generally, you need a lot of pea to get to just that serving of amino acid. What you inadvertently can concentrate as well are the metals the natural levels of lead and arsenic that are just in plants. So this is a known phenomenon. People have quantified the amount of heavy metals you get in protein supplements, and the plant proteins are always the biggest offenders. Now, if I may, one last comment on that is, I think it's interesting, once again, to note as we look back in time, not back enough to explore the theories of evolution, but just in previous generations, particularly in Asian cultures, it's fascinating to me to look at these cultures that have relied on plant proteins to various degrees, although I'm unaware of any that relied exclusively on them. Like, for example, those who would make tofu. It's interesting to me to note that around the world, South America or Asia, when they were relying more heavily on plants, they would always engage a process of fermentation. Fermentation is so powerful because it makes foodstuff much more absorbable. By fermenting the soy, for example, you have eliminated not only metals, but also anti-nutrients like the phytates and the oxalates. They get cut back. They get eliminated basically through the fermentation. And so now all of a sudden, when you're eating that fermented plant matter, now you can in fact digest much, much more of it than you would have otherwise. So to me, there's an opportunity that if someone wants to, or in their mind has to get their protein from plant sources, then my encouragement would simply to be eat it the way humans used to eat it, and in some places still do. Get it from fermented sources. If it's not fermented, you're wasting a lot of money and you're getting a lot of stuff that you don't want.
You mentioned Asia, and sometimes we hear about the blue zones in Okinawa and Sardinia in Italy and places in California and so forth, where the prevailing theory around why these populations have centenarians and supercentenarians is actually around their restriction of protein, that we're trying to like clamp down, let's say, on protein, and maybe maybe the thinking around that is when we clamp down on protein, we're going to be clamping down on the mTOR response and clamping down on insulin, et cetera. Why? I'll just ask it.
Have you ever heard me talk about this before?
I
don't know that you have.
I might.
I almost wonder, like, are you trying to wind me up because I'm about to go? The moment you hand it over to me, I'm going to go.
All right. Well, I'm going to wind you up, and I was going to say I'm going to ask the question by revealing my bias, which is, can you tell us why that's a fallacy? Because in my understanding, and I'll let you take it, is that we actually need more protein as we age. Because of some of this anabolic resistance that kind of sets in. So I feel it's a fallacy. But we have like the Dan Buttners of the world and the Victor Longos and like I don't want to like poo-poo, because I respect anyone who's dedicated their life to trying to better understand the human condition and what is the optimal diet for humans. But it just seems not to make sense to me. So with that, I wind you up and I allow you to
now I'm
Yeah.
unspringing. So I have very strong feelings about it because I believe that whether it's deliberate or accidental, data has been horrifically misunderstood or even construed to fit an ideology. So a few things. In humans, we have zero evidence that proves that protein consumption will reduce longevity. There's no conclusive evidence. We have correlational evidence that is all over the board. Even Walter Longo's own work found that there was during their 50s, people who ate the most protein tended to have the highest mortality, which would fit that overall view that protein promotes mortality. But even in his own published data, at around the age of 60, 65, it went inverse. It flipped. And at that point, the people who ate the most protein had the lowest mortality. And that is a theme that has been published across multiple papers, particularly in the recent probably 10-ish years. So suffice it to say, the evidence on humans with protein and longevity is very, very complicated. And there's no evidence to suggest conclusively one way or the other. I would say that part of what's important, as you noted, is that the older we get, the more protein we need to sustain our lean mass. And muscle and bone mass is one of the greatest predictors of mortality. Inversely, people with the highest muscle mass are the least likely to die. Well, good luck maintaining muscle mass if you're not eating a lot of protein. Now, if we leave the humans to the side for a moment and we get more mechanistically into animal models where we can control everything, we can measure them their entire life from the day they're born to the day they die. Animal models like mice who have a slight protein deficiency in their diet will live a little longer than the animals that have ad libitum or free access to protein. So that supports that general idea. However, they also have almost no fertility. They do not reproduce. And that is sort of this irony that, yeah, sure, you can live longer, but what good is your life if you can't, there's no family involved in this. Now, again, we have to be cautious trying to translate the animal studies to the human studies. And these animals are living in a perfectly controlled little box, literally their whole life. And so their muscle mass doesn't matter as much. They're not a human who's walking through the kitchen who stumbles and now has to grab the counter to stop themselves from falling. And if they don't have enough muscle mass, well, they didn't stop themselves. They hit their head, they broke their hip, and now they're going to die. So an animal is so artificial in this regard that it's hard to rely on too much. But I do feel compelled to mention that there are animal studies to show a causality, that with some degree of protein restriction, they did in fact live longer, but there were consequences that now, in my mind...
Was it protein restriction or caloric restriction?
Yeah, that's a very good question. They did it protein. They'd had a protein restriction.
It was just
they
protein.
Lived longer.
Okay.
Mm-hmm.
Okay.
Yeah.
Okay.
But you're proper in noting that the calorie restricted access or a side to it as well, because that also, I believe the findings are essentially the same. Now, however, in the midst of this kind of poo-pooing dietary protein and wanting to avoid it for living longer, we not only have to appreciate the effect of the muscle, but we have to kind of desperately appreciate the fact that with humans and our survival, depending on the maintenance of our lean mass and the maintenance of our brain and the fats that come with those brains, the further to kind of bring it back to the topic we were touching on earlier, the further we're getting from animal sourced foods, the more nutrient deficient we're becoming, not only in nutrients at a kind of micro level, but also just good fats and these best proteins. We don't want to avoid protein in an effort to live longer. Moreover, I guess back to the fertility aspect, in men at least, we know that the further men get from animal-sourced foods, the lower their testosterone levels are and the lower their sperm quality gets. So this, to me, further suggests the fact that a diet that is devoid of animal products is a diet that is incompatible to the human species. And
kind of coming back to, we were talking about, a menopausal woman, let's say now she doesn't have that estrogen protective effect and her fats become a bit more hypertrophic. If we are able to maintain or even add to her lean muscle mass, let's say, then that like one of the things we know about muscle, of course, is it is a beautiful glucose sink, right? It's a kind of independent of insulin, really. It can kind of take glucose up, phosphorylate it, and then it kind of stays in the muscle for the use of the musculoskeletal system. And then now when we have a, musculoskeletal system, we'll say, that can take in excess glucose, then you're negating the need, we'll say, for insulin to kind of pump, like get ready and rev up and get the glucose out of the bloodstream. And we're going to be protecting that fat cell from becoming too big, right? So then we're protecting that hypertrophic effect as well. So maybe you can speak to some of the, we've been talking a lot of science and geeky science, which is just, like I said, I froth at the mouth at this stuff. But I also want to give my listeners some actionable items in terms of, in our fertile, and maybe we can kind of categorize it for women in their fertile and reproductive years, and then our women in their menopausal years. What are some things from a nutritional point of view that we can do to augment, let's say, the disposal of glucose what are the ways that we can use protein and protein supplementation, keeping in mind that you've talked about, protein in nature occurs with fat. Are there certain types of fats that we need to be looking for? And, we talked a little bit last time about linoleic acid and stearic acid, so we won't get into that now, but in terms of pairing fat and protein together. And if you're supplementing, like I supplement with, I train several times a week and I supplement with protein powder. So what might be a good habit that we can maybe get into from that point of view, and then kind of pair that with how and fasting maybe and the ketogenic diet, and then what happens in menopause, like how does that shift for a woman when she moves into menopause?
Yeah. So you really loaded me there, but let me go with it. So you started with muscle, and I am an enormous advocate of resistance training. In fact, to the point that I believe minute for minute, a man or a woman is better served engaging in resistance exercise than aerobic exercise. I stand by that very, very strongly because of the evidence that just suggests how critically relevant muscle mass is in longevity and lifespan and overall quality of life. What good is it living an extra 20 years if you're sitting on a couch or in a bed? We want those 20 years. We want to square off the curve of mortality rather than having this slow decline. We want to stay functional, and then drop dead. And muscle mass is largely the predictor of that phenomenon. And so we need to make sure we train like it. And so I don't mean to sound kind of derogatory by saying it this way, but I will sometimes joke, maybe to my sisters, women need to train like men. And I only say it that way because women tend to have an aversion to actually exercising in a resistance fashion to fatigue. There will be this, I'm lifting these 10-pound dumbbells and I do it 10 times and I'm done. And she didn't even come close to fatiguing the muscle. And moreover, I was making little biceps curls, and I'm actually very opposed to biceps curls. I don't like I don't like isolated exercises like that. I mean, not isometric. I don't like isolated exercise. I like complex movements. But nevertheless, whatever she's going to do it to fatigue. And so if the woman wants to lift a lighter weight, well, then do it to fatigue. Stu Phillips, professor in Ontario, it's funny, we're both, you and I, Stephanie, I believe, are from Canada. I'm from Alberta.
Yes.
I keep invoking these Canadian scientists. He published a paper finding that the level of hypertrophy in an older adult human was the same whether they did a higher weight with fewer repetitions or a lower weight with more repetitions. As long as they went to failure, they had the same degree of muscle growth. Even when they were older, humans are capable of growing their muscles even well into their 60s and beyond, depending on where they had been before that. So a woman needs to appreciate the value of resistance training. I'm deliberately saying resistance training and not lifting weights because they're not. I don't believe they're the same. I resistance train every day. And yet I don't lift weights. I lift my own body in various ways. So I just do body weight based exercises, but I do them at a very high tension and I go to fatigue. That's how we need to exercise in order to promote muscle growth. So that is the stimulus for the muscle growth. But then the next variable is fueling that muscle growth. And that comes to the nutrition aspect. But actually, before I get to that, let me just mention menopause because we were talking about muscle building in women. With menopause, I actually like the way you said it. There's an opportunity for her now at that point, I want to be careful saying this because I think motherhood is one of the most magical things in the world. And I just am so grateful for my wife, who is such a devoted mother. But at that point, her body is her own. Where she doesn't have to worry about growing another baby in it, and she doesn't have to worry about nursing that baby. And so, as you noted, maybe now is an opportunity for her to get a little more aggressive if she hadn't been for whatever reason, and couple that with the fact that she also does not have this fat kind of hyperplastic stimulating effect of the estrogens. The opportunity here would be that with the loss of the estrogens, there's less of a stimulus to make fat cells. And indeed, her fat cell number will start to go down in around her 60s. That does happen in men and women. And I think if an adult can couple that with aggressive lifestyle intervention, then the opportunity is to in fact get leaner than they were before. And so I like that sentiment, and I think that it's an opportunity for the woman, perhaps, or maybe at least that's how it would be nice to look at it that way, rather than just all bad. And that's when then now we couple it with not only with the stimulus for growth, but the fuel for the growth. And the fuel for the growth it's primarily just calories. Make sure that you're eating enough, but fat and protein are a uniquely favorable anabolic mix. That in nature they come together. That's how we should eat them. And not only is the protein providing the building block, like the leucine you mentioned, these amino acids that we need for muscle growth, but the fat helps further with the energy, and it helps us digest and absorb protein better. When people have all heard of bile. Bile is something that's released into the intestines when we eat fat to help us digest fat better. Most people don't appreciate the fact that bile also facilitates protein digestion. And in the absence of bile, like if we're eating protein alone, we will not digest that protein as well. And we'll leave a lot of it in our intestines unabsorbed. We don't get to it. And so another reason why we should have the fat and the protein come together. And the timing of it isn't overly important. Another work of Dr. Stu Phillips is that a lot of people say, oh, you got to get your protein 1 hour after your workout. In reality, it's kind of like a big barn door. It's not a window. As long as you're just getting adequate protein in kind of a daily amount, then you're fine, or even multi-day amount, you're fine. You're getting enough. But I feel so strongly about this fact that protein and fat should come together that it was actually something I wanted to help people with. And so I worked with one of my brothers, actually, and we created, I just feel compelled to mention it, a meal replacement shake. And it is a meal replacement, and it is built on fats and proteins. The best fats from nature, like ghee and coconut oil and olive oil, and the best proteins and collagen and some probiotics. So I basically wanted to take what I learned in the lab and everything we've been talking about. And so often I talk about these ideas and someone says, okay, great, Ben, thanks. Now what? And this is simply a way for people to make it easy. If they don't have time to plan and prepare a perfectly balanced meal, then they can just sort of get some of this shake on the go. And I won't say any more about it other than anyone who wants to learn more, go to a website called Get Health, and health is spelled HLTH, so GETHLTH.com. Not only can you see all my blog posts, including one I just released today about alcohol metabolism, but also just learn more about the shake. And if you're interested, you can get some there. But it is just, again, built on these two pillars of protein and fat, and each enhancing the digestion of the other and providing the actual essential fatty acids and essential amino acids that the body needs. And then one last comment about fat, because you'd asked about the differences with saturated fat and so on. I'm an enormous defender of saturated fat. It is one of the natural fats. It comes in coconut oil and any animal source fat. And saturated fat, it actually has a gut protective effect. There was a lot of people nowadays are very rationally interested in leaky gut. And it is a real phenomenon where the kind of integrity of the gut becomes a little compromised, and you get little gaps between the gut cells that allow stuff to kind of seep through from the intestines into the body. It is known that saturated fats will seal those little gaps between the cells, whereas polyunsaturated fats actually aggravate it and open those little gaps. And those are the fats that primarily come from the industrial seed oils like soybean oil or canola oil, etc. A lot of people are becoming very aware of seed oils, and I won't say any more than that in this context. But even at the level of the gut, these high levels of polyunsaturated fats will promote the gaps between gut cells, increasing the likelihood of developing leaky gut, whereas saturated fats have the opposite effect, sealing those gaps up, allowing the gut to have a very high level of integrity and make sure the only things that get in are the things we want.
I love what you're saying here. And I want to come back to your meal replacement for a moment. I know that you're so humble that you won't do it, but I'm going to do it because I think that this is important. So when we're thinking about aging well, we've talked about having a mechanical signal, right, to the musculoskeletal system. So you're lifting weights, or resistance training, as you said, working the muscle, again, quoting Stu Phillips, and it doesn't have to be muscle failure, by the way, but you are approaching muscle failure. So that can be done on a 30 rep set with 5 pounds, let's say, or like a lighter weight. It can also be done with a 5 rep set, obviously with a much higher weight. So you can kind of oscillate, depending on where you are in your cycle. If you're still in your reproductive years, kind of based on the hormonal environment, you might train differently through your cycle. When you're in menopause, you can kind of choose whatever sort of tickles your fancy, and you're sort of freer in a way. It's like a second spring, really, menopause, in that you're not so bound by this optimization for fertility, which is a vital sign in women. So we have this mechanical signal, but then there's also a metabolic signal, right? So it's this protein consumption and fat. So just kind of looking at the specs of this health code that you've put together, there's 400 calories, 27 grams of protein, optimal balance of healthy fat, fiber, vitamins, minerals, 50% of the daily value of 25. I'm just reading this off the side here. Daily value of 25 vitamins and minerals in each serving. So this is actually really, and kind of talking about meal timing for a moment, a lot of people in the morning, right? Typical breakfast is usually like kind of some sort of dessert. It's like a muffin, right? It's cereal. So I actually think that this is a nice way, if you're short on time or skill, right? If you're like, I don't know how to make eggs, or I don't know how to do poached eggs or whatever, this might be a really nice replacement, let's say, for the lack of skill or the lack of access or time, and you can get the proteins and fats that you're wanting.
Oh yeah, you stated it perfectly. Yeah, my view and my hope when we developed it was that this would be an option for people when they can't, and when they don't have time to make some good steak and eggs or cook a roast, in these really deeply nutritious foods, which are the best foods. Then here's an option where they know they don't have time for lunch, so they put 2 scoops in their shaker bottle, they take it to work, and they'll put in the water and prepare it at work when they need it. That's one of the main ways I actually eat it, for example. It's just so convenient. So it's a nice, convenient way to ensure you're getting the right nutrition and not kind of knocking your body off the metabolic track that you're on.
Love that. So we'll make sure that the link, the Get Health link, is in the show notes, so people can easily click through. Also make sure that your YouTube video on glucagon is in there. And then a link to your book, Why We Get Sick. Any last thoughts? This has been such a geeky, like the best conversation. I'm so happy that we were able to do this again. But any sort of last thoughts, if there's one takeaway that there was a lot, we went into a lot of weeds today, but if there's one or two, let's say, takeaways that you really wanted people to leave this podcast with, what would it be?
Yeah. I'd say one comes to mind as we've mentioned fasting, and I'm such an advocate of fasting. It is such a wonderful way to just reset and almost immediately begin to improve your insulin sensitivity. As people are becoming so enthusiastic about fasting, which again, I endorse, I think it's very important for people to know that how you end a fast is more important than how long you fast. I just see this happening more and more, where people start to use fasting as almost a kind of glamorous binge purge cycle, where they fast for 36 or 48 hours, and then they get so hungry, they don't really have a plan, and they just binge on junk food. They eat themselves full to the point of bursting, and they're sick. They are ashamed. They literally feel sick. They don't sleep well that night because they're digesting and their body temperature is so high. Their heart is pounding because of all that digestion. They wake up the next day, and all that shame basically tells them, you can do better today. Do it again and cleanse yourself. And then they get into the same habit. And so my strong recommendation is how you end a fast matters more than how long you fast. So have a firm plan. And Health Code, my shake is a great way to do it, or any other number of items that someone could eat, but have the plan in place and recruit help to stick to it. Because fasting is incredibly powerful, but it needs to be coupled with well-formulated diet and particularly well-formulated meals on the back end of the fast. And maybe that last comment would be breakfast, as you noted. It's particularly tragic in my mind that a person overnight has cleared all their food out. Their glucose and their insulin levels have come down to a nice low level. As insulin comes down, fat burning starts to ramp up. And then what do? The moment insulin has come down, we immediately spike it with these high starchy, high sugary foods. And the conventional common eating pattern nowadays is that they spike the insulin for breakfast and they do it again for their mid-morning snack and then their lunch and their afternoon snack. And a person is essentially spending every waking moment in a state of elevated insulin, ensuring that they're not burning fat and further promoting insulin resistance. So be very, very smart with breakfast, or to say it again, just be smart with how you end a fast, even if it's just your nighttime fast.
Yeah, I like that. I actually, depending on the length of the fast, of course, often I'll counsel people to break it with some type of liquid as well, because we've had some stomach shrinkage and like having a full meal just might be too uncomfortable for them. So a liquid fast would be appropriate there as well. Again, with some proteins and some fats, as you've said. Yeah. All right. I hope that you enjoyed that conversation as much as I did. For more conversations like Dr. Ben Bikman and mine, please click right here at this video coming up right at you right now.